Smith chart, basic applications of Smith chart, series on transmission line theory, lecture number 4.20. Smith chart is a graphical tool highly useful in solving problems pertaining to transmission lines. Its main attraction is in being able to give answers to various transmission line problems without requiring to do lengthy or complicated calculations or computations. It is able to give SWR over the line. It is also able to give reflection quotient over the line. From this graphical tool, one can also determine impedance over the line at an arbitrary point. It is also possible to find the locations of voltage maximum and voltage minimum over the line. Several more things are also possible from Smith chart. In fact, it makes the calculator redundant as far as solution of transmission line problems are concerned. In the present session, our focus is how Smith chart is used in solving various transmission line problems. In almost all uses of Smith chart, the starting point is drawing a circle. This circle is called constant SWR circle. Another name is also there, constant rho circle. What is this circle? It is a circle drawn on the chart with one of the horizontal line as a center and one to the load point as radius. The impedances represented by various points over the SWR circle denote impedances of line at various points within a length of lambda by 2. This point connects chart with the line. We all know chart is circular in shape. Inside the chart, each and every point represent certain impedance. Not only that, each and every point is also associated with certain value of reflection quotient. What he says is the impedances represented by various points. SWR circle is drawn like this. Circle means several points. Various points over the SWR circle denote impedances of the line. Here is a line, impedances of the line at various points within a length of lambda by 2. Distances over the line are represented by angular distance around the chart. Total circumference are 360 degrees corresponding to line length of lambda by 2. Hence, a pass through 1 meter distance over the line corresponds to a rotation of 2 beta degrees. First point is, out of 3 points in this slide, first point is, it gives information regarding how to draw SWR circle. Next 2 points, they try to connect the chart or SWR circle over the chart with the actual transmission line. The point at which the constant SWR circle intersects the horizontal straight line, right side of the center, corresponds to SWR of the load. For each different value of SWR, there exists a separate circle with a different radius. Constant SWR circles intersect horizontal line at points 1 by rho and rho. Notice, this is the chart, this is the horizontal line, this is SWR circle. This circle intersects the horizontal line at 2 points. Left of 1, right of 1, right side, left side, 2 points. These points, they give 1 by rho and rho. Left point gives 1 by rho, right point gives rho. These points also denote line impedances equal to Z0 by rho. Here, this point represents Z0 by rho, whereas right point represents Z0 multiplied by rho. From the given load and characteristic impedance of the line, how to find out VSWR using Smith chart? We take up this issue first. What to do to find VSWR is, from load impedance and Z0, find out normalized load impedance ZL by dividing given ZL by Z0 and locate load point over the Smith chart corresponding to ZL. ZL is impedance. It can be written as R plus JX. Identify a circle whose value is R identify a arc whose value is x, and intersection of the circle and the arc gives the load point, which represents ZL. From the given load and CI, find normalized load and locate load point P over the chart. This is the starting point to find VSWR from ZL and Z0. Now, draw SWR circle. See, load point is somewhere here. We call it by P. Now draw SWR circle with the center O and radius OP. See, center of the chart here, you can find a number 1 here. We call the center by O. Now center over O and radius from O to P. Draw a circle. This circle is a SWR circle. This circle intersects the horizontal line at 2 points. Left side once, right side once. Now you concentrate on the right side here. Let us call this point Q. Against this point Q, one can find a number. It is usually more than 1. That number is SWR. SWR over the line. It is the one that is required for us. Or one can use SWR horizontal scale provided at the bottom of the chart. See, normally the Smith charts, they also come with certain scales at the bottom. Several scales. One in them is SWR circle, SWR scale. You transfer this distance OP over to this scale to find out SWR. So this is the way, this is the process, this is the procedure by which one can find SWR over the line just by mere observation. No calculator is required, no computations are required. Now we move to another task, that is locations, finding locations of first Vmax and first V minimum. After locating the load point, draw SWR circle. As already mentioned, this is the starting point in many of the usages of Smith chart. Load is given, characteristic impedance is given. From that you have to find out normalized load impedance, and this normalized load impedance has to be transferred to Smith chart. It gives load point P. Once P is available, one can draw SWR circle without any difficulty. Now actual process. To find locations of first Vmax and V minimum. Using wavelength scale provided over the periphery of the chart from P, measure the distance of one infinity segment of horizontal line giving Dmax, and also 10 segment of horizontal line giving D minimum. In both the cases, measurement should be done in clockwise direction over SWR scale circle. These two distances, Dmax and D minimum, give distances in wavelengths of the first maximum and first minimum from the load. They are also distances of current minimum and current maximum respectively. So what to do is, the procedure is, in simple terms, this is the Smith chart. Now let us suppose load point is somewhere here. This is the load point. This is center O, load point is P. Now draw SWR circle. What he says is, you measure the distance from point P to, let us say this point is Q. And let us also suppose this point is R. From P, measure the distance to Q in clockwise direction. This distance gives you Dmax, or distance of voltage maximum from the load. And from P, you continue measuring the distance through Q up to R. This distance gives D minimum. That is distance of first voltage minimum from the load. This D max, D minimum. To find these distances, one can use the outermost scale that is available. Outermost scale is 0 at the leftmost point, and by the time you travel half of the chart, it is 0.125. Actually, it is in terms of lambda, 0.125 lambda. So this scale, you can use this scale to measure the distance between P to Q. It gives Dmax, that is distance of first voltage maximum from the load. And you can measure also the distance from P to R in clockwise. That distance gives D minimum, or distance of first voltage minimum from the load point. Here is shown. This is load point P. From P to, if we call it Q, from P to Q, measure the distance using outermost scale. That gives distance of voltage maximum from the load in wavelengths. If you continue measuring distance up to R, then that gives D minimum. So this is D max, D minimum. D max means voltage max distance, D minimum means voltage minimum distance. Now we go to another use or usage of Smith chart. How to find RC over the load? See, gamma is reflection coefficient. It is complex quantity. It is related to load impedance through ZL minus Z0 by ZL plus Z0. In this way one can find out. But ZL is complex, gamma is complex, Z0, if we consider lossless lines, it is real. But the point is, right hand side it is complex division. So it is difficult. We need to use calculators. Calculator may not be available. But if we have a Smith chart, and if we know how to use a Smith chart without doing any calculations, without the help of calculator, we can find out very easily. So this aspect we consider now. RC, reflection coefficient over the load. For that, what we have to do is, from the given data, locate load point. How? ZL, Z0 both are given. ZL by Z0 gives normalized load impedance, and locate normalized load impedance over the Smith chart. That gives load point P. The distance of this point P to the center of the chart gives magnitude of RC, which can be read from RC scale provided at the bottom of the chart. Another method is draw a radial line from O to P and then extend to outermost circle of the chart. R equal to 0 to Q. The ratio of OP to OQ gives magnitude of RC. To find the angle of quotient, use scale provided over the periphery for the purpose. In fact, it is angle θ1 from one infinity segment of horizontal line to radius OP. It is positive when load is inductive, negative for capacitive impedance. One can use protractor scale provided over the periphery for this purpose. So, in simple words, the idea is this: locate P over the chart. Let us say somewhere here. P is somewhere. It can be lower side of the chart also, but okay. Let us say it is here load point. This is O. Now, one way is you transfer this distance OP over to the gamma scale that is provided at the bottom of the chart, and from that scale one can read out magnitude of the reflection quotient. This is one way. Another way is simply extend this OP to Q to periphery of the chart. Let us say it is Q. This radial vector, if we extend, let us say it meets the end of the chart at Q. Now, using a scale, you can measure OP, you can measure OQ. OP by OQ, this ratio gives magnitude of reflection quotient. Either way, either one you can use. Regarding angle of reflection quotient is a complex quantity. It has magnitude as well as angle. Phase angle can be found using the scale that is provided here. Measure the angle from one infinity segment. This is one infinity segment. From here, you just measure that angle using the protractor, that scale provided over the periphery for this purpose. Then that gives reflection quotient, magnitude as well as angle. The operations are shown here clearly. This is the center of the chart. This is the load point P, and it is extended to the periphery of the chart and to Q. Now, OP by OQ gives magnitude. Now, the angle measured from one infinity segment, this segment, to load point, that is reflection quotient. Here, another example is also considered. Let us suppose load point is here, P prime. In such case, what you have to do is you extend this radius further to the periphery of the chart. Let it be Q prime. OP prime by OQ prime gives magnitude, and the angle of the reflection quotient you have to measure as usual from one infinity segment, that is θ2. It is negative in fact in this case. Next, RC at D from load. See, here is a line. In the previous consideration, the process is explained how to measure or how to find out RC over the load. This is load exactly over the load. How to find out RC? Now, we consider a point P which is at a distance of D from the load. At this point, what is reflection quotient? This process is explained right now. Locate load point P and draw constant SWR circle. Move a distance D over this circle clockwise to identify a point P prime on the circle. From the distance of this point P prime to the center of the chart O, which is same as P to O, as the line is lossless, magnitude of RC can be found. Angle of RC θ2 can be found from angle between OP prime with one infinity segment of horizontal line. Note θ1 is angle of RC over the load. What he is trying to tell is, this is Smith chart. Now locate load point. It is somewhere here. Now draw SWR circle. Now from P, move a distance D over this circle in clockwise direction. In clockwise direction. Let us say the point P here is at a distance of, let us say, 0.01 lambda. Now from here, you move 0.01 lambda distance over SWR circle. How do we know that we have moved 0.01 lambda? You use the outermost circle, outermost scale. Lambda scale is available. Using that scale, we can move. Now let us, now you are here. Let us call it P prime. Now extend radial vector from O P prime to periphery. It may be giving Q prime. Now O P prime by O Q prime gives magnitude of reflection coefficient and angle measured from one infinity segment to this radial vector OP prime gives angle of reflection quotient. So here is explained, this is the point, load point. But I want reflection quotient at a distance of D from load point. So I have to move a distance D for the SWR circle. P prime has come. Now extend OP prime to OQ prime. OP prime by OQ prime gives magnitude of reflection quotient. Angle of reflection quotient is the angle measured from one infinity segment to the radial vector, that is theta 2. Here it is indicated as theta 2. Notice in both the cases, magnitude of reflection quotient is constant. That is, see, here is the line, here is the load. We are considering lossless line. Lossless line. So over the lossless line, magnitude of reflection quotient remains the same. Whether it is here or whether it is here, the magnitude remains same. OP by OQ is same as OP prime by OQ prime. But angle changes. Here reflection quotient is having one angle, here another angle. Here the angle of reflection quotient is theta 1. Here, which is this point which is at a distance of D from the load, angle of reflection quotient is theta 2. Now let us suppose we are interested to know the impedance at a distance of D. In the previous slide, our discussion is at a we considered a point and that point is at a distance of D from the load. At this point, what is reflection quotient? Now in the present slide, the issue is at this point, what is impedance? For that procedure is locate load point and draw constant SWR circle. This is common to all the problems we are considered so far. Move a distance D over the circle clockwise, not clockwise. Why clockwise? The point is towards source. You are here. Towards source, you have to move towards source means clockwise. So identify a point P prime on the circle. Now identify R and X values of the circle arcs passing through this point, which gives normalized impedance at a distance D from the load. By multiplying this impedance with the Z0 of the line impedance in ohms can be obtained. This process can also be used to identify the type of load at any point over the line. So point is this. This is the smooth chart. First identify load point. Let us say somewhere here. This is load point. This is O or 1. Center of the chart, it is usually denoted by O, and there you can find 1. Now what you have to do is draw a SWR circle through point P. Starting from P, move a distance D over the SWR circle. A distance D. This is distance D. How do we know that you have moved the distance D? You can use the scale that is available over the periphery of the chart. Here scale is available. It starts 0 and by the time you reach on the other end it is 0.125. That scale. Use that scale, clockwise scale, and move a distance D. After a moment you are here. Call this point P prime. Now through this point P prime, one can notice a circle passing. A circle and also an arc. If no circle is passing exactly through P prime, you identify a circle which is passing nearest circle to P prime. That circle is associated with certain number. That number is actually normalized resistance. The arc is also associated with that number, that is normalized reactance. Normalized resistance plus normalized reactance, that gives J normalized, gives the normalized impedance. If you multiply it with Z0, we will be getting actual impedance of the line at a point which is located at a distance of D from the impedance. This is the way, here it is explained. This is the point. Now distance D, you move over SWR circle, a distance D you have to do. Now P prime has come into being. Through P prime, one circle passes. Let us say some circle like this passes, and also an arc also passes through it. Circle is associated with a number. That number is normalized resistance. The arc is associated with number that gives you normalized reactance. Resistance, reactance at the point, which is at a distance of d from the load. Now, one more aspect also we consider: stub length, which can give a susceptance equal to plus or minus B. Shorted line, shorted lossless line, open circuited lossless line, their input impedance is pure reactance or susceptance. Sometimes we need, in fact, in stub matching, single stub matching, double stub matching techniques are there. While implementing those techniques for load matching purposes, we need to know the lengths of stubs which can give certain amount of susceptance. That particular aspect. What is the length of a stub that can give plus or minus B susceptance? That aspect now we discuss. In case of shorted stub, the start from rightmost point of the chart and move clockwise direction over the periphery until arc denoting plus or minus B is met. In case of opened stub, the starting point is leftmost point of the chart. The distance moved gives the length of the stub. Now, before going further, let the problem be made clear. I want certain susceptance, plus or minus B. This is the susceptance I want to connect to a line, of course, for load matching purpose. This susceptance is simulated using transmission line. Now the question is, what should be the length of the line? Whose input admittance is plus or minus B? This is the question. I repeat, what is the length of the line whose input admittance is plus or minus JB? This is the question. How to find out the length? The process is, in case of shorted stub, the stub can be shorted or open circuited. Open stub, usually shorted stubs are used. Short circuited stubs are used. In case of shorted stub, start from rightmost point of the chart. The procedure is like this. Suppose I want a susceptance equal to plus JB from a shorted stub. Then what is the length? This is the problem. For that, what you need to do is take a Smith chart, start from rightmost point of the chart. This is rightmost point of the chart, and move clockwise direction. You move clockwise direction over the periphery until arc denoting plus or minus B is met. Suppose if you want plus B, then move until plus B is met. Plus B is available over the upper portion. Let us say it is somewhere here. So you have to move from rightmost point to how much distance you have moved. That distance you can find from the scale provided over the outer side of the chart. Let us suppose you want minus JB. Minus JB means starting point is this, because shorted stub means starting point is rightmost point. You have to move until minus JB, minus B is met. See, here you can find arcs. For example, here is an arc. This arc is associated with minus 1. Here is an arc. This arc is associated with the plus 1. See, if you notice the arc here, it is associated with some number which is more than 1. The arcs which are left side, they are associated with numbers less than 1. Similarly, here also, more than 1, left side means less than 1. Bottom side, they assume negative values. Upper side, they assume positive values. So point is, if it is a shorted stub, you have to start here and move until the arc which represents the susceptance that you want, that you are expecting from the shorted stub. And until you meet that arc, you have to move. The distance you moved gives the length of the stub. If it is opened stub, suppose you are using opened stub, suppose then the starting point is this, leftmost point. The starting point is leftmost point of the chart. The distance moved gives length of the stub. When the required susceptance is negative, then the shorted stub length is found smaller than opened stub. When the required susceptance is positive, plus B, then shorted stub is found larger than opened stub. Here is shown. Suppose you want to find out a shorted stub length, that gives minus JB. minus JB. Then you have to start here, you have to move until you come across an arc which represents minus B. Okay. If it is opened stub, you have to start here and you have to move clockwise. Movement is always clockwise. So this A represents when the requirement is negative susceptances. B represents when the requirement is positive susceptance. So these are some of the basic operations that are involved in the application of Smith chart for solving various transmission line problems. This is what I want to share with you for now.